In this video, we will be looking at graphical representation. Right? You need to use graphical methods to represent distance, displacement, speed, velocity, and acceleration. Meaning you are supposed to know how to sketch speed time graph, velocity time graph, acceleration time graph, distance time graph, displacement time graph. Right? And you are supposed to be able to find the gradient of displacement time graph, know what it means, find the area and gradient of VT graph, know what they mean, and even for the cases where the acceleration is not uniform. Can you describe the motion of the ball here? Can you tell if the acceleration is constant or uniform? And what is the direction of the acceleration here? Our eyes are not very good at judging acceleration, right? So let's watch this video to help us see acceleration. The red dots represent a constant time interval. So you can see the displacement is larger as you move down the slope. Right, so how do we determine acceleration using the motion diagram which you've seen earlier? Right, you can see we can find the velocity just by the displacement because between two red dots is the same time. So you can see the final velocity is larger than the initial velocity. Right, this is the initial velocity, this is the final velocity, and the change in velocity is here, and change in velocity divided by time is our acceleration. Okay, so from here you actually can see the direction of the acceleration, okay, which is same as the change. Okay, and how is ST graph, displacement time graph, obtained from motion diagram? So this is a motion diagram, right? You mark the car position every second, right? So you can see that this car is moving at constant velocity, 1 meter per second, right? Therefore, you can see if you mark it, at first it is traveling 1 meter per second, right? So at displacement 1 meter at 1 second, then at 2 meters, 3 meters, 4 meters, so on and so forth. If you join all the points, you get a straight line. So this is a displacement time graph, right? It shows you the position of the car at different times. Okay, in a second graph here, right, the car is moving at a greater velocity, 3 meter per second instead of 1 meter per second. So every 1 second it travels 3 meters, right? So you can see that I same mark out the points 3, 6, 9, 12, join all the points together and you get the graph in this displacement time graph. Right, so you can actually very easily get a displacement time graph from the motion time graph, right? The position at each time, right? That is the motion time graph. And from here, you can see at a higher velocity, the graph is actually steeper, right? And this is something you should already know since secondary school. Now, if we have a car that is moving with a changing velocity, you can see it begins with 1.2 and 1.4, 1.6 increases until it moves at 4, right? So if we mark the position again, right? Using displacement at the position of the car at each second, right? So this is at 1.2 meters, right? And so on and so forth. If you mark the points, you will find that you get a curve. Okay, and if you draw a tangent at different points, you to find the gradient of that point, you find that the gradient actually correspond to the velocity of the car at that time. Okay, so now gradient 1.2, 1.4, 1.6, right? It is same as the velocity here. So in other words, the gradient of a displacement time graph represent the velocity. Right, and we call this velocity instantaneous velocity because it is a velocity at that particular instant or particular time. Right, and you can find the gradient. Gradient is given by ds dt. So this is a quick revision. You need to remember this. This is very basic. Right, let's look at displacement time graph now on page 6. Right, you have this displacement time graph to show how the body displacement vary with time. So again, you need to analyze separately the magnitude. Okay, how far from the start point? The start point is A. Okay, so if it's 6 meters here, means it is 6 meters away from the start point. The sign, okay, the sign indicate direction. Remember, displacement is a vector, and the gradient, which is the velocity. Okay, let's look at this graph from A to B. From A to B, you can see that the body is moving towards B with a constant velocity, right? Because it is a straight line, gradient is constant. So gradient is instantaneous velocity. So since velocity is constant, it is moving at constant velocity. And how do we find this value? You just find the gradient. So 6 minus 0 divided by the time 6. Right, so it's 1 meter per second. Right, let's look at section B, C. The body is at 6 meters, displacement of 6 meters throughout this 6 seconds. So in other words, it is stationary. Or you can look at the gradient. This gradient is 0. So gradient 0 means velocity 0, right? So it is stationary. Lastly, section CD, right? The body is decreasing, right? Its displacement is decreasing, meaning it is moving backwards now, right? So it is moving backwards and make a U-turn at C, okay, towards D. So velocity is -4. Find the gradient. -4 minus -6 divided by the time is -2.5. Right? So you can see that it is actually moving in the opposite direction here. Okay, because velocity is negative and you can see displacement decreasing, so it must be moving back. Okay, at point 0 here, okay, it just means that it have gone past the starting point, right? So it start a U-turn at point C, continue to move back to its original position, position A, and then it continue to move in the negative direction further back 4 meters. Right, now how do we transform a displacement time graph to velocity time graph? Right, so first we already found the gradient earlier. So the gradient is constant, right, which I found earlier. So So it will VT graph, the velocity will be a constant value here, right? Right. So you can see the gradient is constant, so it should be a horizontal line. And for BC, the object is at rest, so the velocity should be zero, right? So it should be zero at this whole point. And remember at C, it starts to U-turn, so it becomes negative, but it is still a constant velocity. So it should be negative constant, right? So you get a negative horizontal line, right? So the red line represents the velocity time graph. Okay, so now let's look at the displacement time graph we have earlier, right? And we need to transform this to a VT graph. So what you do is very simple, right? You find the gradient at various points, and that will be the value of the velocity. You mark them, and you can join this line, right? So in this case, you can see that the velocity increases constantly, right? Actually, from here you can tell velocity increases by 0.2 meter per second. Okay, so therefore the velocity should increase in a straight line, and gradient of this should be zero point 0.2. Okay. Okay, so with that, you should be able to, from the displacement time graph here, plot the velocity time graph, right? As I said, use a gradient at a point. So gradient at 10 second is 2. So at 10, the value should be 2. Okay, so you mark this value. Okay, and as I mentioned earlier, the velocity is increasing by 0.2 meter per second for every second, right? So the gradient is zero point 0.2 meter per second for every second. So it's meter per second squared. Okay. And from here, you can see the area. Actually, we want to find this area. It is the half times base times height. So the value is 10. Right. And what is this significant? The significance of this value is, you look at this, the area is 10, and we look at the ST graph, the displacement is 10. So in other words, the area of a velocity time graph represents displacement. Okay, so you need to be able to also convert a VT graph to a ST graph. As I mentioned earlier, you use the area, right, to mark the value, right? So now you reverse finding the area at each second and mark the points on the displacement time graph, you can get this graph, right? This is one way to do it. Okay, now let's look at velocity time graph. Figure 2.7. Same thing, we analyze three things, right? The magnitude, the value of v, how fast the object is moving, the sign, whether is it positive or negative, that is the direction of the movement, and the gradient, right? The gradient is how fast velocity is changing per second. So that is actually rate of change of velocity, which means it is acceleration. Of course, for VT graph, the area represents the displacement, right? Okay, remember, instantaneous velocity is a gradient of the ST graph. Right, let's do a conversion now, or transformation from VT graph to ST graph. Right, so from P to Q, velocity is increasing and positive. Okay, so ST gradient is increasing and positive. So I should be able to sketch here that the gradient is increasing. Okay, so it's curving upwards, right? And it is positive. Okay, so it is going up, not coming down, right? Because velocity is increasing and positive. Okay. Next section, QR. QR, you can see that velocity is constant and is positive. So positive velocity means positive gradient in an ST graph. So this is a positive gradient and a constant gradient, right? Because V is constant. Next part here, RS. RS is velocity is decreasing here, but it is still positive. Okay, so the gradient is decreasing, right? It should get more and more horizontal, the gradient, and it's still positive, so it should still be going upwards. Okay. Next, ST. Can you deduce what is happening here? Yes, ST is now V is negative for ST, right? Which means gradient must be negative, right? And the value is actually increasing. So V is becoming more negative, so the gradient should become more negative, as you can see here, right? So you should be able to transform a VT graph like this into a ST graph like this. Okay, now let's transform VT graph to AT graph, acceleration time graph. Right? Remember, gradient of VT is the instantaneous acceleration. Right? So from A to B, gradient is constant and positive. So A should be constant and positive. For QR, gradient is 0. So acceleration should be 0, right? And constant. So it is a straight horizontal line. For RS, right, gradient is negative. So A should be negative and it's a constant. So it is a horizontal line. Same thing from S to T, right? Okay. Okay, so the label here should be P, Q, QR, and R, T. Okay. Okay, so you can look at this again, right? How we transform VT graph to AT graph. So you can see the gradient here is constant, so acceleration is constant. Velocity gradient is positive, so acceleration is positive. Right? So in this case, page 8, velocity to acceleration, right? You can see that the acceleration should be decreasing because the gradient is decreasing, right? And V is positive, so A should be positive. Okay, so that is velocity is increasing. Okay, right? Velocity is increasing. You can see the value is still increasing at decreasing rate, right? So it tells us that it is a positive gradient, positive A, but it is a decreasing A, okay? Because decreasing gradient. Let's look at example 3. Right, a stone is thrown upwards at the top of the cliff. After reaching its maximum height, it falls past the cliff top and into the sea. Okay, so it reached maximum height and then it fall past the cliff top and into the sea. So the graph shown how the vertical velocity of the stone varies with time. Right, R and S are magnitude of the area of the two circles. What is the height of the cliff top? Okay, so what you can do is this, you look at this, velocity is decreasing until it reaches 0. So this point must be a maximum point, maximum height, right? So And the gradient throughout is constant, right? That should be our acceleration due to gravity, 9.81, if there is no air resistance, right? So you can see, sketch a diagram here. So S is actually the displacement, the object moved to the maximum height, and R is the displacement from the top, from the maximum height to the sea, right? So that's R. So we are finding the cliff top height, right? And that is R minus S. Answer is D. Okay, right? Let's look at work example 4. Tennis ball is released so that it falls vertically to the floor and bounces back, taking velocity upwards as positive. Which one of the following graphs best represent the VT graph? Okay, so first we look at this. Tennis ball is released. So release means that it has zero velocity, right? So when you release something, you don't push it, so it has zero velocity. So the answer must either be B or C. Okay, it falls vertically, so it is moving downwards, but upward is positive. Okay, so as it falls downward, it should be getting more negative, right? So the answer should be C, right? It bounces back, so there should be a portion of time the direction is positive upwards, right? So answer is C. It has confirmed that. Okay, let's look at the next part, the acceleration time graph. Right, gradient of Vt, remember, is actually instantaneous acceleration. Right, so let's look at AB. This part is constant gradient, so we should get constant A. Positive gradient, so positive A, right? You should be very familiar. So can you, in your mind, sketch the graph now and see whether you get it correct? Did you get it correct? Good, right? So if we sketch the AT graph now, we can put in the shape of the graph, but you have to find the values. Okay, so this 4 is actually the gradient here, 20 divided by 5, right? So 20 divided by 5, right? Similarly, you find the gradient for the second portion, or the third portion rather, okay? And put in the values. Work example 5, bouncing ball. A steel ball is released from rest. Again, release means the initial velocity is 0 at a distance above a rigid horizontal surface and is allowed to bounce as shown in the diagram below. Taking air resistance as negligible and downwards as positive, right? So downward is positive now. It is up to you to decide upwards or downward is positive. But in this question, they specify downward is positive, so you have to follow this convention. Sketch on the axis provided is corresponding graph representing variation with time t of displacement, velocity, and acceleration. Which one should we draw first? Should we draw displacement, velocity, or acceleration time graph first? Question, which one is easiest to draw? Right? So if we look at this, downward is positive, there is negligible air resistance, so only weight acts on the ball, which means acceleration due to gravity is the acceleration, and it will be 9.81 throughout, except when it is in contact with the ball where it's going to bounce. right? So during contact with the ground, large acceleration in opposite direction, in this case upwards. Okay, so A should be negative, very large magnitude. Okay, because there is a force upwards, therefore the acceleration is upwards here now. Right, so if you sketch an AT graph, it will look like this. Right, when it's falling, it is always a horizontal positive value 9.81 because downward is positive. Okay, so the rising part is the same because the weight is still downwards, so acceleration due to gravity doesn't change its direction. So you can see like this portion, there is a negative A, negative A. This is where it bounces. So you see the ball falling, bounces, then it rises up, reach a maximum height, falls again, and then bounces when it reaches the ground. Okay, right? So the VT graph gradient is acceleration, and since acceleration is positive and constant, mostly except for this point, we can sketch the velocity time graph. Right? So here the gradient should be 9.81. Gradient is positive because A is positive. During impact, the gradient is very large, okay, almost infinite, and it is negative gradient because A is negative at this point, right? Then you get a positive gradient again. So remember this portion here, the ball is falling, hit the ground, first impact, this part it is rising, okay? So rising gradient should still be 9.81. Reach a maximum height, it begins to fall, gradient should still be 9.81. Then it hit the floor again, that's where the gradient become negative. Okay, very steep gradient here to indicate a large negative acceleration. Okay, and bounces up, right? So gradient is positive again. Okay, so this is the motion which I have explained just now. Right? Notice area X should be equal to area Y. Why? Can you explain? Remember, this is the moving upwards. This is moving downwards, which means this point is the maximum height. So the height of rising should be equal to the height of falling, right? Therefore, the area should be equal. Okay, now from from VT graph, we should be able to get a ST graph. Okay, and remember in ST graph, the gradient is the velocity. So V is positive here at the point of release, V is positive. So ST gradient should be positive and V is increasing, so gradient should get more steep, right? So it's positive, upward sloping and getting more steep. Okay, at this point, V is negative, right? The gradient here is very large, most infinite, so the gradient here, you can't really find the gradient here because it's infinite, okay? Right? So next, for this part here, after first impact, V is negative and magnitude decreasing, okay? So V negative means gradient negative, and V is decreasing from more negative to less negative. So my gradient should become from more negative to less negative. Okay, at this point, maximum height gradient should be 0 because velocity is 0. Okay, so and then it repeats itself. Right, so this is the most tricky part here on impact. So on impact, you just have to join the graph. Actually, it's not very smooth here, it's a sharp turn, right? Because the value here takes a very sharp turn also, right? So the velocity change very sharply, so the gradient would change very sharply. Okay, you can actually go to the link on page 9, right? There's also a QR code there. You can actually play with the applet. I can't do it here, but you go to a website, you can do it, right? And you can see how a bouncing ball give us this graph and this graph. Okay, do it on your own. Okay, now we just want to summarize quickly the relationship between ST graph, VT graph, and AT graph, right? So if you differentiate ST graph, or the gradient rather, of ST graph will be equals to the velocity, right? So if you integrate VT graph to get the area, right? So area will help us find the value of displacement. Area of VT graph represent displacement. Similarly, if you differentiate velocity with respect to time, that means you use the gradient of VT graph, you will get the acceleration, right? And similarly as well, if you find the area of AT graph, that will be the value of the velocity. Okay, now pause the video and look at the three graphs. Test yourself to see if you are able to derive one graph from another. So you start from derive VT graph from ST graph and then derive AT graph from VT graph. Right? Later do the reverse. Given AT graph, can you draw the VT graph from here? And then with this VT graph, sketch the ST graph. Okay, do in both directions, test yourself and compare with this answer. Okay, you are now ready to do concept worksheet. This is very important because it helps you practice transformation and to see whether you can get it correct. Your tutors will go through the answer with you, right? So it is important that you do this to make sure you are correct. This foundation will cut across other topics as well, right? So please do so for page 25 to 27, right? And you can already now do tutorial questions 1 to 9. That's all for this video. See you.